start. Good morning, everybody. Today we see the linear integrated circuit. What is the use of this IC? Linear integrated circuit. Linear integrated circuit. This is also called as OPAMP. This is operational amplifier. Why this is called operational amplifier? Because this operational amplifier can be used as an integrator, as a summer, differentiator, then you have subtractor, comparator, and these are the applications of OPAMP. You can use for different applications. That is the reason it is called operational amplifier. These applications are where you can use the OPAMP. One is your adder. Second one, subtractor. Third one, you have integrator. Fourth one, you have differentiator. Fifth is your anti-lock. And logarithm. These are the applications. That is the reason it is called as a operational amplifier. Next we see this, the symbol of the op-amp. Symbol of the op-amp is like this. It is a triangle where 6 pins are used. This is pin number 7. This is used for positive VCC. This is pin number 4. This is used for negative VCC. And basically these 2 pins are used to bias the op-amp. Okay. For any operational amplifier or any transistor or any amplifier, you need to bias the transistor to keep it in for proper functioning of the op-amp or amplifier. Then 6 number pin is used as the output. 2 number pin is used as the inverting terminal, and 3 number is used as a non-inverting input. And rest of the pins, let's say pin number 1, pin number 8 and pin number 5, these are used for different purpose. Pin number 8 is not used, it is no connection pin. Pin number 5 and pin number 1 is used to verify the offset which is produced within this op-amp. The next is you have the IC pin number. This is DIP IC, then it is 8-pin IC. These are the pins, and here the raw pin there. This is 1 number pin, this is 2 number, this is 3 number, this is 4 number, this is 5 number, 6 number, 7 number, and 8 number. Okay, this 1 and 5 is used for offset purpose, to reveal the offset. Pin number 7 is used for positive VCC. Pin number 4 is used for negative VCC. Pin number 2 is for inverting terminal, where you can apply the input to that terminal. Pin number 3 is non-inverting terminal. And pin number 6 is your output voltage, from where you can get the output of this op-amp. Okay, this is symbol for op-amp. Certainly 741 we consider here, LM741C, and this is there are n number of IC, different number of ICs are manufactured by various semiconductor company, but we will see this 741 in detail. Now this is being symbol, this is IC pin number, it is 8-pin IC, and these are the respective pins are shown here which are related. And pin number 5 and 1, this is used to adjust the offset which is produced within. When there is no input, some voltage is produced to offset this output voltage for giving the input at 0 voltage. So that offset is used, offset resistor is used in between pin number 5 and 1. Okay, next is you have characteristics of, next is characteristics ideal op-amp. One is input impedance. Input impedance. Second one, output impedance. Output impedance. Third one, you have voltage gain. Voltage gain, and fourth one, you have battery. These are the four characteristics over which we can understand what are the basic characteristics of op-amp. And this is we consider for ideal op-amp, later on we will see for practical op-amp. This input impedance, ideally it should be infinite. Output impedance, ideally it should be 0. Voltage gain, ideally it should be infinite, and bandwidth should be infinite. These are the ideal characteristics as far as output, as far as op-amp is concerned. But practical op-amp, it doesn't hold this value as far as practical op-amp. For the characteristics of practical op-amp, input impedance should be very high. Output impedance will be very low, and voltage gain will be very high, as well as bandwidth should be very high. Input impedance should be in terms of mega ohm, then output impedance in terms of ohms, then we have voltage gain in terms as far as practical op-amp is concerned, and if it is open loop, it will be very high, it will be in 2 lakhs or 20,000, it will be in that range. And bandwidth is concerned, you should have any operational amplifier or amplifier as far as voltage is concerned, bandwidth should be very high. Okay, so that you can cover all different ranges of the frequency which you are going to apply for the input signal, which you are going to apply for the op-amp for amplification purpose. Then next we will see the characteristic you have seen ideal op-amp is internal blocks of the op-amp. As we have seen, this is the block diagram schematic of the or symbol of the op-amp. This is 7 number, this is 4, 6, 2 and 3. These are the input V1 and V2, and we are taking out. Within this op-amp, there are n number of transistors are involved to build the op-amp, but we will not go into detail of the circuit level of circuit details of this op-amp. But what are the different blocks which are present within this op-amp? Say we have first stage. This is first block. Let's say you have second block and you have third block. These are the major blocks which is present in this op-amp as far as block wise. This first, this is second, and this is third. Here first block will be the differential amplifier. Second block will be the voltage amplifier. And third will be your output stage amplifier. And normally this output stage amplifier will be the push-pull type. What is the purpose of push-pull type? Because it will satisfy it will take care of whatever load you are going to connect at the output side. This differential amplifier, it will take the difference which you are applying at this point. Let's say V1 is minus 2 volt and V2 is equal to let's say 3 volt. So these two voltages will be applied here. Okay, and whatever the common, which is let's say somebody is talking, that same signal will be the common mode which is surrounding normal amplifier. In normal amplifier, what happens? You have this transistor, then you have this VCC, and this is you have ground, and you have connected V in here, and you are taking the output at this point. In this case, there are two inputs. This is also used as an operational amplifier or amplifier. Here, this is used as an amplifier, but this is single input is there. Suppose you have applied voltage V is equal to 2 volt or 2 millivolt. Okay, this is you have 2 millivolt, which is you are going to amplify the signal of 2 millivolt. But sometimes what happens? The surrounding noise will also impact, or it will be added into this 2 millivolt. Let's say 2 millivolt, or noise is let's say 0.1 millivolt. So the total voltage will be 2.1 millivolt. In this case, 2.1 millivolt. And if the gain of this op-amp is let's say voltage AB is equal to let's say 100. We are interested in amplifying this signal, which is we want to amplify actual signal, or this is the our useful signal, and this is the noise signal. If you use this 2.1 volt at the input, if you apply the 2.1 including actual signal as well as noise signal, then Vout will be AB into VE. Okay. Then let's say AB is equal to 100 into VE is equal to 2.1 volt. So this will be how much it is going to be? Let's say 100 into 2, it will come around 210 volt. Okay. Here the actual signal is 2 millivolt and 0.1 is the noise voltage. So total voltage you got 210 something volt. But as far as we are interested in 2 volt, if you consider actual signal, Vout will be AB into VE, where VE is the actual signal. Let's say this is 100 into 2. So this will be 200 volt. In first case, noise is also amplified. In second case, only 200 volt is there. So difference in first case and second case, that is 210 minus 200, it will be 10 volt, which is amplified. And this is not our actual signal, which is amplified. But this is noise signal, which is added to this terminal of this input of this amplifier, and this is signal is amplified by 10 volt extra. So you are having the output voltage of 210 instead of 200. So 10 volt difference is because of the noise. And this fact you cannot remove this signal as far as this amplifier is concerned. So we moved from this amplifier to this amplifier. In this case, what happens? Let's say same example we take here. Let's say this is 2 volt is the actual signal which you want to amplify. Okay. And this is V, and V into let's say 3 volt. This signal is applied at negative terminal. This signal is applied at positive terminal. Let's say some voltage is added 0.1 millivolt here. This is let's say 2 millivolt plus 0.1 millivolt. Here also 3 millivolt. Okay, 3 millivolt plus you have 0.1 millivolt, because these two terminals are located at the same place, so the noise signal will be same at both terminals. So at the output side, what will happen? Let's say this is 2 millivolt plus 1, 2 millivolt plus 0.1, it will be equal to 2.1 millivolt. At this point also 3 plus 0.1, this will be 3.1 millivolt. Okay. Now we have this is 2.1 and this is 3.1. At the output side, we need to take the difference between these two. Let's say difference is I am putting gain of this AB is the gain of the open loop gain of this op-amp. Let's say it is. Let's say for understanding purpose, let's say it is 20,000. Okay, this is open loop gain of the op-amp. It is much. Normally it will be very high, but for practical understanding purpose, we will consider here 20,000. Now output Vout in Vout is equal to AB into V into or V2 minus V1. This is equal to 20,000, or bracket in bracket is 3.1 minus 2.1. So at the input of both input of the op-amp, it will be nullified or it will be cancelled at the output side. So in this case, it was 10 volt which is amplified to 0.1 million input noise voltage. Here also noise is present, but because of the difference which is you are taking out the output, difference will be get amplified, and whatever the common which is input at the input terminal 1 and 2 which will get cancelled. So you will get how much it is 20 into this 2 will be how much it is coming to be? It is coming to 1 volt. So you have 20 volt. These are the theoretical value. As far as practical value, you will not get this much voltage at the output. Okay, so this will get saturated. Let's say this will get saturated to some practical value. Here, let's say you have applied plus 10 volt and here you have applied minus 10 volt for biasing purpose. In this case also, even the gain of the op-amp is gain of the transistor is much more. So you will not get the output voltage which is beyond your limit. Let's say applying for understanding purpose, let's say AB is equal to 200 and Vin is equal to let's say 2 millivolt. By calculation, theoretical calculation, V out will be AB into Vin. Then what will happen here? AB is equal to 200 into 2 millivolt. So this will come around 200 into let's say 2 millivolt into 10 raised to minus 3. Here also millivolt is there also. Here 10 raised to minus 3 you need to consider. Here also 10 raised to minus 3 you need to consider. So how much voltage will be? It will come around, it will be 0.1 volt. So these are the practical within this limit it will be possible. If you increase the gain much more, which is in this case 20,000 volt it is coming. So this is not practically possible. But what in this case or in this case also, if the voltage changes or voltage is amplified much more, it will limit to or this limit there will be limit by positive VCC or negative VCC. So let's say in this case you have 10 volt here VCC and here negative 10 volt. So even if you apply small voltage at the input side, it will be amplified by because the gain of this op-amp is very high. It will be amplified no way. But theoretically it is coming 20,000. Theoretically, but practically it will saturate to plus 10 volt and minus 10 volt. So it will be 20 volt, max to max 20 volt. Ideally, it will be lesser than that because of some losses or drops in the transistor operational or operation in operational amplifier. So the restriction will be 20 volt. As far as theoretically it will go to 20,000, but it is not so as far as practical op-amps are concerned. Okay. The next one is we will discuss about inverting amplifier. We will discuss about inverting amplifier, non-inverting amplifier, and we will do some analysis for that. Let's say this is your op-amp. This is you are taking the output at this point. You are inverting negative, this is positive, and these are two for biasing positive and negative. These are for biasing purpose. But here, let's say you have connected the input, and let's say you have connected input here, and this is grounded, and this is grounded. You are taking, still these are in open loop condition. If you apply V in here, let's say V in, and you are taking the output, and AB is the gain of this amplifier, then output will be minus AB into V. Okay. Actually, V instead of V, it will be AB minus AB into V2 minus V1, where V1 is equal to Vn. But V2 is equal to 0 here, you have applied grounded, so it will be AB into V1. And V1 is equal to VIE, that is equal to minus AB into V1. Okay. So whatever voltage you are applied, it will be amplified, but with negative polarity or with 180 degree out of 180 degree phase shift. This is called inverting terminal. And these inverted terminals still it is in open loop. Another example is this is called inverting terminal or inverting amplifier with open loop. they are applied some input, let's say V2, and it is connected at the ground. In this case, the output will be, in this case, output will be AV into V2 minus V or V1. Here V1 is equal to this. Let's say this is V1 and this is V2. V1 is equal to 0, so this will be AV into V2 or AV into V. In this case, voltage will be also amplified, but there will not be any phase shift in the output waveform. Okay, so this is normally called non-inverting amplifier. This is previously what we are seeing inverting and non-inverting. These are in open loop. What is happened in open loop? In open loop, the gain is very high. In open loop, the gain is very high. That is the reason it is normally not used as a practical amplifier. But for that purpose, there are two types of feedback. Either negative feedback or positive feedback is used. And we will solve this example with considering feedback. Inverting amplifier. You have the OPAMP. This is negative, this is positive. And now you have connected some feedback between negative and positive. Negative terminals and output terminal. Let's say this is, you have connected some input V in here. And this is grounded. And this is connected at ground potential. And this is your V out. Okay. As we know that the input impedance of this OPAMP is very high. Input impedance of the OPAMP is very high. So the current which is entering at this point is I in is equal to 0. So this will be I1 is equal to I1. And here this potential is virtual. This potential will be 0 volt because of the ground. In this case, what happens? This terminal will be at virtual ground. Upper terminal is virtual ground. So this potential at this point will be 0. So now the current, if you apply the KCL at this point, I1 is equal to minus I0. Okay, this I1 is equal to, then I1 is equal to V in divided by R1 is equal to, I is equal to minus V out divided by RL. Then V out divided by V is equal to minus RL upon R1. This will be the gain of the amplifier. As far as non-inverting amplifier is concerned, and in this case, gain will be V out divided by V is equal to RL upon minus RL upon R1. Okay, चलो